Why is it hard to translate complex math models into robust engineering code? Imagine trying to convert a detailed blueprint of a complex machine into a functioning physical prototype. The process involves more than just copying measurements. It requires translating intricate ideas into a language that machines can understand and execute reliably. This challenge becomes even more pronounced when dealing with sophisticated mathematical models used in engineering. Mathematical models often involve highly abstract concepts such as differential equations, nonlinear systems, and multivariable interactions. These models are designed to capture real-world phenomena with precision, but their complexity can lead to difficulties when implementing them in code. For example, solving nonlinear differential equations numerically requires careful consideration of stability and convergence. Small errors in calculations can lead to significant deviations from expected results, making the code unreliable. Another obstacle is the inherent difference between mathematical notation and programming languages. Mathematical expressions are concise and elegant, but translating them into code demands meticulous attention to detail. Programmers must choose appropriate algorithms, discretization methods, and data structures to accurately representing the mathematical concepts. This process often involves approximations, which can introduce errors or reduce the fidelity of the model. Furthermore, complex models frequently involve multiple interacting components that must work seamlessly together. Ensuring that these components communicate correctly and maintain consistency over time is a significant challenge. Numerical stability becomes a concern, especially when models involve stiff equations or requiring long-term simulations. Engineers must implement safeguards to prevent errors from compounding, which adds layers of complexity to the coding process. Computational efficiency also plays a vital role. High-fidelity models can demand substantial processing power and memory. Engineers need to optimize code to run simulations within reasonable timeframes without sacrificing accuracy. This balancing act often involves advanced techniques such as parallel processing or adaptive mesh refinement, which add further complexity to the coding process. Finally, real-world data used to validate these models can be noisy or incomplete. Incorporating such data into the code requires robust algorithms capable of handling uncertainties and variations. Without careful design, the code may produce unreliable or inconsistent results, undermining the entire modeling effort. In essence, translating complex mathematical models into dependable engineering code involves navigating a landscape filled with mathematical intricacies, computational constraints, and practical considerations. Each step demands precision, expertise, and a deep understanding of both the mathematics and the engineering context.